Greetings, my name is Claudia and I will present to you the work named Correlation between Quality Evaluation Metrics and the detection results in panoramic X-ray images using deep learning. And I am going to start by talking about panoramic images. Among the dental X-ray images used to complement the clinical examination and to plan a proper treatment course, panoramic images are one of the most requested exams. And this is basically because these images allow the visualization of the whole set of teeth and the surrounding bone structure, while also helping in finding hidden caries, cysts, tumors, bone loss, among other pathologies. Although it is true that dental X-ray images are a primary tool for a dental health professional, the reading and interpretation of the images, especially panoramic images, is a time-consuming and complex task, which can lead to errors due to fatigue or lack of experiences of professionals. Because of this, efforts have been made in order to design computer-assisted analysis methods that can help in reducing the workload of professionals. Since a crucial part of these analysis systems are the automatic localization of anatomical structure, in the field of dentistry, most neural network-based works focus on the detection and segmentation of teeth. Although it is true that the results achieved by deep learning method have been increasing since the introduction of convolutional neural networks, any system for the automatic localization of anatomical structure must obtain results comparable of the professionals in order to allow its clinical use. In achieving this high level of accuracy is still a challenge for object detection algorithms based on deep learning. But since the results achieved by a deep learning method not only depends on the configuration of the network, the architecture, but it also related to aspects like pre and post-processing, data augmentation, and hyperparameter optimization, there are works in which authors use some techniques in order to improve the results achieved by their chosen architecture. One of them is the work presented by Murad Matsu, in which they use a preprocessing technique to automatically detect the mouth gap in panoramic images in order to reduce the search area. Meanwhile, the work presented by Chen and others, they use 3 post-processing techniques in order to improve the detection results in periapical images using faster RCNN architecture. And finally, Tuthoff and others perform the tuning of parameters related to anchors, the IOU of the non-maximum suppression algorithm, and the prediction score threshold in order to improve the results of T in panoramic images when also using faster RCNN. Since it has been proven that using a preprocessing technique is a differentiating factor between deep learning algorithms that use the same architecture, in this work we were interested in finding the correlation between image quality metrics measured in enhanced panoramic images and the detection results of different deep learning architecture. The images used in the experiments consist of 300 images of a public dataset. This public dataset of 1,500 images is divided into 10 categories. Three of them we can see in figure number 3. And the difference between these categories is that they contain images with or without 32T, with or without restoration, with or without implants, and with or without appliances. After that, we proceeded to trim the panoramic images to exclude toothless regions using as reference points the green sections here in figure 4. And after that, we proceeded to perform the annotations for T detections by drawing a minimal rectangle named bounding box around each 2 in an image. And finally, the 300 images were split into 192 for training, 48 for validation, and 60 for testing. The image enhancement techniques used to apply to the panoramic images as a pre-processing technique were 2 smoothing with edge preservation filters, the anisotropic diffusion and the bilateral filtering, and 5 contrast enhancement algorithms. The brightness preserving B-histogram equalization, the contrast limited adaptive histogram equalization, the geodesic reconstruction, multi-scale morphological contrast enhancement, the multi-scale top hat transform, and the quadri-histogram equalization with limited contrast. In figure 6, we can see a comparison of an original image with an image enhanced with one IET. And for more detail about these techniques, please refer to the paper since we don't have enough time to describe them here. The image quality metrics used to evaluate the outcome of the IET were the absolute mean brightness error, which gives us the difference between the brightness of the input image and the output image, the peak signal to noise ratio, which measures the amount of noise and distortion introduced to an image, the structural similarity index measure, which take into consideration the difference between the brightness, the local contrast, and the correlation between the 2 images, the global contrast, the contrast improvement ratio, which measures the difference between the local contrast of 2 images, the entropy, which quantifies the amount of information in an image by providing the number of bits needed to encode this image, and the edge preservation index, which measures the ability of a technique in preserving the edges present in an image. The deep learning architecture chosen for this work were the faster RCNN, Cascada RCNN, RetinaNet, the fully convolutional one-stage object detection, and YOLO V3. The first step of the experimental setup consisted of selecting pre-trained models and weights from detection model for each chosen architecture. After that, we performed hyperparameter optimization using the original images, and then we fine-tuned a total of 8 models for almost 100 epochs. And why 8 models? Because one of them was trained with the original images, and the other 7 were trained with an IET applied to the panoramic images as a pre-processing technique. The inference on the test set was performed by first selecting the base weights of these models by considering the highest mean average precision on the validation set. And after that, we evaluated the performance of the models computing the accuracy, the precision, and their code with an IOU greater or equal to 0.5. With the image quality metrics and accuracy, precision, and recall measure, we then computed the cross correlation between these values. And then we have the results. In table 1 we have the IQM results, and in table 2 we have the model's performance. In this table we can see that the QHELC model outperformed the baseline model in 3 out of 5 architectures, and the bilateral filtering performed better than the baseline model in 2 architectures. While BBHE model present the worst performance in 4 of 5 architectures. In Table 1, we can see that the QHELC technique slightly increases the global contrast of the images and has one of the best values of SSIM and PNR and the second best value of IPE. While the BBHE technique is the technique that most changes introduced to the global contrast and local contrast of the images and present a low value of SSIM, PSNR, and IPE. While the correlation results are shown in the form of correlation heat maps, where we can see that the Cascade RCNM followed by RetinaNet are the two heat maps with the strongest correlations, while the heat maps of FCOS and ULV3 present really weak correlations between the metrics that we chosen in this work. And if we look back at the correlation heat map of Cascade RCNM, we can see a positive relationship between the accuracy and the precision with SSIM and PS and R metrics, and a negative relationship between these two metrics and AMBE, the global contrast, and SIR. This relationship means that an IET that do not introduce much noise or distortion while also preserving the brightness, the global contrast, and the local contrast of the images will tend to have better results of accuracy and precision, which was what happened with the QHELC technique, but as we saw in the previous slide. And the opposite was the output of the BBHE model, which, as we can recall, was the technique that most changes introduced the global contrast and the local contrast of the images, which had a negative impact on the accuracy and precision of the model, achieving the worst performance in 4 out of 5 architectures. And finally, according to the results that we found in this work, we can conclude that using an enhancement technique not necessarily improve the detection of TM panoramic images using deep learning methods. Not all deep learning methods show dependence on the enhancement of the input image. No, not at least the enhancement technique that we chose in this work. That an IET which preserves better the features and introduces the less noise possible to the images will tend to reach better performance. And then a high increment in the global and local contrast will have a negative effect on the detection results. An example of this is what happened with the BBHE technique. And in contrast, if the increment in the global contrast is small, as it is with the QHE technique, this will be beneficial for the detection results. And with that, this presentation ends. Thank you very much for your time.